Welcome everyone to the post-launch session. So we have been at so today we will talk about harmonic analysis on hyperparalysis.
I would like to thank our visitors for giving me an invitation to talk about something new. So, today I just want to say that I was lecturing somewhere in ISC. But the thing is, most of the students are really concentrating more on writing rather than understanding. And I just do not want that. And so please try to understand things rather than understand. So the goal of my lecture series is just to develop or support for your analysis on the symmetric space, the self-product models only. So for that reason, actually, we will develop some kind of knowledge and between the so-called point guidance and using some analogy, we will define a geometric Fourier transform, which is called as Helgason Fourier transform. And we will prove a transfer theorem for that, and you will prove a Fourier inverse. Okay, so, I will begin with this definition. A closed subgroup G of GLC is called a matrix equivalent. So, an example is GLNC, GLNR, SLNR, SLNC. These are the matrices, examples of matrices. And let G be a matrix 0, then its Lie algebra of G is defined to be easy. This is collection of all n by n complex matrices. So that e to the power dx belongs to MX for all t belongs to R. So this is a very simple exercise. So that Lie algebra of G is a real vector space subspace of MX. Okay. Now, actually, in mathematics, whenever you write LU, actually we write those things in capital letter, and its Lie algebra actually is written in small letter, and that is also in German too. So, for instance, this is GLNC. So its Lie algebra is written in this small GLNC. And similarly, if it is SLNR, this is a very small SLNR. Lie algebra is written in small SLNR. Similarly, just write down this one. So Lie algebra will be written in small SLNR. You can verify that this GLNC is nothing but MLC. This is an exercise. This SLNR is here. This is X not MLR. The place of X is here. And similarly, this is here X not MLR. So that X plus H transpose. So these things I will not use in lead theory. But the thing is, I will use this terminology. I will throw some words like Lie algebra. So, okay, you know that this C cap is really, this is a notation C union infinity. And this is the extended complexity, or this is the management. This group GLQC is acts on C cap. I have moved transformation. So what is action? Because if you take A, B, C, comma D belongs to GLQC. And it will act on Z like AZ plus B by CZ plus 2. So this Z belongs to C. And this action is not helpful because if A, B, C, D dot Z is same thing as minus of A, B, C, D. So, and another thing is, so you know that in complex analysis, you also consider the straight line also a circle, right? That is a really circle passing through it. So probably I should. Okay, I am erasing this one. So it's circle in C cap, where circle in C or a straight line in C. And this straight line in C, usually people call that this is a circle passing through infinite. And what is the justification? Justification is the thing is secured with the Riemann sphere, and if you project the circles in the Riemann sphere by a stereographic projection, you get actual circle in C or straight line in C. So, and okay. So we are actually interested in a particular subgroup of GI and that is really simple. So you all know this definition of a circular. Okay, and it has a particular subgroup. This is K, this is SO2, and this is SO2 that contains all the rotation matrix K theta, basically as cos theta, sin theta, minus sin theta. And this K theta is a rotation in R2 and in rotation of angle theta in R2 in the anti-clockwise. And this K is isomorphic to the closed interval 0 to pi, comma modulus to pi. That is basically S one. So this is K is a really compact solution. So K stands for compact solution. And theta are going to take theta is a topological expression. Okay. Now there is a second subgroup of important subgroup of G that is really diagonal matrices with positive diagonal matrices. This is called A, and A stands for abelian. Okay. A stands for abelian subgroup. And since this is collection of all 18, which is really of this for e to the power t 0 0 0 minus t plus 1. By the way, this symbol, this colon and equality, is we will use this symbol when we define something. So this is the definition of it. And A is really isomorphic to R, and T going to AT is a group isomorphic. That means this is A is isomorphic to R as a group, and it is also topological. So this A is abelian. So and another thing is, okay. So exercise. This is a very simple exercise. Take that this real geometry is really T0, 0 minus 2. So that T1 to R. Now, okay. Now if you take any element of A, that is of this one something like A.
This guy A there, you the power 80.
What?
So first take it right.
Yeah.
You not e to the power 80.
No, I am not saying e to the power 80. This is a notation for 80. This is just this matrix I am defining it. This A is different from this A. Okay, let us make this B. It's clear, Master. Okay, so this B is equal to 0, B is greater than 0. So B will be of the term from 80, right? E to the power t. Because B is positive. Okay. So exercise, this is very simple exercise. So that B as of A is equal to of this one T0, 0 minus T0. Now since you take A comes to A, so that means A is of the one something like 80. Okay? Oh, you define this log A. Log A by this matrix T 0, 0 minus. So what I am saying, this 80 is really into the power T 0 So I define this log of 18. This matrix actually P 0 0 minus. If you look at this exponential of log of 18, then that is very now this element log of 18 is a matrix, right? It is an element of Lie algebra, and we will identify this element with a real number. Okay. So, and it will be clear from the context. So when we will use this idea. So what I am saying, log of 18 can be thought of as a matrix element as a real number. But that identification will be clear depending on the context. Okay, so that is what is there. So A, K, and I have defined A. Similarly, there is another group N. This is N stands for the important group. Now this N, the collection of all Ns, which is of this part 1s 0 2. So this is a really upper triangle matrices. This is an upper triangle matrix with diagonal entries 4. And this group is isomorphic to R. And this S going to Ns is a group S. So we will use these notations throughout my lecture. So now actually there is also another subgroup of circular, that is very much P. P is equal to collection of this matrices of this form A, B, 0, A, B plus. So that A is determined. So this is now clearly this A subset of P, this is subset of C. And this A is also subset of P. Now take any element P belongs to P. So this, so take this any take P belongs to P. The P is of the form. This is really A, B, 0, A. This is P, so this is my P, P is equal to this. And this can be written as something like A 0 0 A. And this is 1 B by A and 0. And this decomposition is very unique. This decomposition is unique. So this belongs to and this decomposition, okay, this actually if you look, actually this decomposition is really continuous. What does that mean? If you denote this by A and N, this A and N depends continuously on P. Is it clear? So what I'm saying. I'll so what I'm saying that observation any event belongs to P can be uniquely P is going to be with A belongs to A and N belongs to A. Moreover, this Now, similarly, I can write this P equal to the inverse. This one AB 0. And this first element belongs to the second element. So that also, so that any element P belongs to P can be written as P is equal to of the form P can be written as N with A belongs to N and N belongs to N and A and N equals functions. Okay. Now one small exercise. If you take this thing 80 NS 80 inverse, that is really 8 is equal to 2 years. So this actually you can check it. This is very simple mind. So I am leaving this exercise. So this exercise so that because so this exercise goes. A normalizes. Now I think the ratio between yeah, semi-direct, but this is not direct. I hope by this time you remember this. So, let each is going to this. This Z belongs to C, so that imaginary part of the is greater than 0. So if this J belongs to H and G belongs to circular, then this GZ, G dot Z belongs to H. We can show that. Okay. We can show that this is exercise. So that means self were action of now you want to really analyze what the action of the self were on open action. I want to stabilize of I in so this is GI. What is GI? By definition, this is G belongs to the self. So that G dot I is so let this G is equal to A, B, C, D. It's 1%. G dot I is equal to I. This is we can only A, B, C, D. So I is equal to that is immediate A equals B by C equals B. Equal to I. assuming that G is belongs to a cell product, so that means Z belongs to determinant of G is 1. This is like S square plus B square. So that means Gi is nothing but your K. And what is K? Integrate SO. So now G dot infinity is infinity. That means by definition G dot infinity equal to AB, BD, plus A by C is equal to infinity. And that's so that C is equal to 0. You can know C is equal to so what we will get this thing. So that will show that G infinity. So G infinity will be A, B, 0, A. But the thing is here A belongs, A is not equal. So that means G infinity is really just the symbol P disjunct union minus P. So we have calculated just stabilizer I, and that is equal to, and we have calculated stabilizer for infinity, and that is P. So now we want to look at the action of cell product. Now take any element of A. Take this thing 0, A, 0, A. So this element belongs to A. And how does this will act? It will act like this. If you plug in the data, if you use the definition, that this will be this here. And this is nothing but this is dilation. Dilation. So that means if you are putting this upper half plane picture, upper half plane, and this is say, and this is my point. If you take this thing Z, and if you want to find what is the K orbit of J. That means you have to look at you have to apply every element of K to this point J, and since this is really A square J, so that means you will get A orbit of Z will be just a ray that will pass through J. And it will start from 0. Is it clear? So, what I'm saying. See, the thing is, if you take any element of and dot Z, it will be a square. And you want to find what is the orbit of A orbit of Z. And so for that reason, you have to vary A over all A greater than 0. And so that this is my, you will get exactly this the ray which starts from the origin 0 and passes to this point J. Okay, so these are really my A and B. So that's these are really my A and B. Similarly, if you look at any vector of n, say nx, and this is a 1s, 0, and this z. So I will get this z plus s, and this is translation. Okay, so this is very long. So this is my z. So z, n orbit of z will be this horizontal line which is parallel to the real axis. So similarly this. So these are the areas. Now what will be k orbit? K orbit is really what cos theta, sin theta, minus sin theta. Is really what cos theta is minus sin theta. Sin theta is cos theta. So it is not really very easy to see, but we will carefully. And for that reason, we have to go to the disk picture. We will do that. But before that, we have to derive something. So, our first thing, so this two picture will say that the SL per option on H will be transitive. Okay, so what so clear? G option is transitive. So this is my imaginary lines here. Okay, this is my point I here. So choose any point Z here. So you can draw the array, okay, which passes through origin. This J. And you can draw the so-called horizontal line which passes through this point. Is okay. So that means this point, this intersection point, is in the n orbital pi. So this is basically something like n s dot I. Okay. Now if you apply at this point, z is in the a orbit of n s dot I. So that means z is equal to very what? Is something like 80 n s dot I. Okay. So that means every point z is in the p orbit of I. So this says that every point, so what I have shown, plus every point j belongs to S called z belongs to x. There exists p belongs to p, so that this p dot r is equal to z. Now, so let suppose z is equal to really x plus I, and p is really what? So that p is equal B. Okay. So that means P dot Z will be what? P dot Z is okay. P dot I. So that means this is we will say that A B 0 that I equal to x plus I. That you will get this will be a square I plus AB equal to x plus. So that means so this implies if you this implies a square is equal to y and AB is equal to x. That means give me A is equal to square root of 1 and B is equal to x by 1. So this P is uniquely determined by this Z and P has this part x root of x by root y 0 and 1. So the conclusion is what? Conclusion is conclusion. For any Z belongs to X, there exists a unique P, and that P depends upon Z. There is a unique PZ belongs to capital P, so that the same P of Z that I is equal to what? This is equal to Z. And what is the expression of P of Z? P of x plus IY is equal to root y x by root x by root y till what by y. So that means, and this thing is also true, and Z going to the PZ is our expression from H to P is now is continuous. Thus, you can see this is clearly continuous. Now, I want to do something else. You also have a
Minus P is also there. Minus P is also there.
Apart from
Minus P is also there. If you
but minus P will not be in the by definition. What is the question?
I'm saying minus P is also there.
Minus P. So by definition, P is what? A is 0, 0, A inverse.
Oh, you are taking both possible.
Yeah. Okay, so so what I will do? Listen this thing with the dark attention, because this is the thing which you will need this. Who are silent. belongs to this Z means XI. Let J is equal to then G dot I. Okay. By this conclusion, so there exists a unique P that really depends upon Z, and that depends continuously A on Z. That is unique P, so that P dot I is equal to Z. But P dot Z is equal to what? This is equal to G dot I. Right? P dot I is equal to G dot I. So now I can take P that side. So P inverse G dot I is equal to I. So that means this P inverse G is this other stabilized I. So that means P inverse G belongs to maybe K, because I have proved that stabilizer of I is nothing but K. So that means this implies, so let us write. So this implies P inverse G is equal to get K for some K dot. Now G is equal to Z. Now this P is unique, therefore K is unique. Since P is unique, therefore this implies K is unique. Now this P continuously depends on G. P continuously depends on Z, and Z is nothing but G dot I. So that means P also continuously depends on G. I am saying since G going to G dot I is continuous, and this P is continuously depends on Z, so therefore P will continuously depends on G. Since G going to G dot I is continuous, therefore P depends, and that is right, and Z will be it is continuous. So this implies P continuously depends on G. So if P continuously depends on G, then K also continuously depends, because K is equal to GP, K equal to P inverse. So this implies K continuously depends upon. So what I am getting? I am getting this. I am getting after this G is equal to K. So that is starting with G is equal to P. So every G belongs to G can be uniquely written as G is equal to Pk, which P belongs to P and K belongs to. So moreover, P and K continuously now I told you that this P is equal to A and every element of P can be unique written as something like element of A and element of N, and that decomposition also continuous. So if you will use that P is equal to An and every element of P can be uniquely written as element of A and element of N, and A and N can be continuously depends on P. So you will get that G is equal to A and K in A. So we will use this. Let us write this. Okay, let us write the statement for this decomposition. NA can be. So since thus and this in A can be continuously so now we will get to us our combination. This is nothing but K. So that what we have got that G is equal to NA. So we want to get that G is equal to K. So if you will import the element of G, then you will get K. But I am saying that G belongs to G. So that means this G inverse. Okay. So G inverse as a NA decomposition. So G inverse can be written as N1, A1, K1. And this N1 and A1 and K1 are unique. If you will take this inverse both sides, so G will be K1, A1 inverse and N1 inverse. And you call this K1 inverse as K. And this A1 inverse as A and N1 inverse as K. This K belongs to K and A belongs to A and N belongs. So that means G belongs to G is K, and that means G is equal to K, and this is continuous. So you can, okay, so you can write this type of thing. I am not very right. So you can write that this thus every G belongs to G can be unique written as G is equal to K. With K belongs to K, A belongs to A, and N belongs to A. And that, and K, A, N continuously depends on G. So you can write on your own. Now, if G is equal to K, so I define okay. I define this K part of K bar G by this K. This A bar G, I will use this like this and N bar G is complete. So this is because B can be written as B. K bar G, and N bar. So this, what is K bar? This is the K part of, if you become, if you write the Gauss order decomposition, G is equal to K. This K bar G is the K part of that element. A bar G is the A part, L bar G is. So remember in the beginning I defined something called log of A bar G. Define this log of A bar G, or to define X. Really do not confuse with this upper half plane. This H is different. So H is log of A bar G. And this A bar G is what? This is really exponential of H0. Identity. So this, I told you in the beginning that log of A bar, log of any element, log of A can be thought of as a matrix as well as a real number. So therefore Hg also we will think that is an element of real number, or we can identify with that of real number. So using this notation, we can write this G as, this is K bar G, and exponential of S. Okay, so this is how you are starting. Now we want to go into this picture. So you know that the upper half plane is conformally equivalent to the open unit is, and that conformal equivalence is given by a collector. So next, this is a notation for D. So that Z is the collection of all the elements so that all the existing. So this is the upper half plane. And this upper half plane to this upper unit is, so there is a map. This is called a map. CZ. CZ is a really one. Z minus I is Z%. So this will map this boundary, this real line to this boundary of the disk. And this point is what? C infinity. This is C of I. And this point is given C of 0. So, and this is 0. So, C of I is equal to 0. So, this is the thing. Now, this C is also a means Mobius map. And if you look at this matrix C, this is what? 1 minus I. There's a little 1 I. This is, I am using the same notation. But that is okay, I believe. So C dot J is really what C. So this C is a matrix. So this is the matrix. Okay, so now this is my upper plane stage, and this is, there is a map G, upper G belongs to a cell node. So G acts on its by this mobile transformation. So from H to D there is a map. Okay, that is also a mobile transformation that is given by this C, and this is given by this C. D. So if you compose this map, G, so that will be also a mobile transformation, but that will be given by this C inverse. This will be given by this part C. And okay, so G tilde is equal to C, G, C. The C is this matrix, 1 minus I, 1, 2. This is really CG, same birth. So that G comes to C. Now, so what is this group? Exercise. So this is a simple computation, so I am leaving with it. Exercise. So G tilde, you can calculate this. This is the collection of all matrices of this form A, B, A bar, A bar. And so that A, B belongs to C, and this mod of A bar square minus mod of B bar square is equal to. So it has a name. This group has a name. This is really called SU1. So why it is called SU1? I will not explain that. But you take this as a definition. So SU1, is PC. First thing. Second thing is, so you take this matrix K theta. So the second thing, these are all exercises. So let K theta tilde is really to the power minus I theta. 0, 0 to the power. So that, okay, this is the thing. Let's take a look. If you calculate this thing, C, K theta, C inverse is a really K theta. So this is also an exercise. You can do that. Now, one thing. So K theta actually this represents a rotation. Theta in R2 in anticlockwise direction. So look at the action of K theta tilde in the complex plane. So if you look at this, so K theta tilde Z, this will be really e to the power minus 2I theta. Okay. So this is actually action of K theta tilde. This is in Z. So action of K theta tilde is really a rotation by angle Z or it is C. C is rotation by angle 2 theta in the clockwise direction. This this thing is since there is minus y theta here, so what you will get what K theta tilde Z, the same thing as K theta plus phi, because there is a 2 factor here, and this K tilde theta plus phi, simply this is nothing but minus of theta. And this is x minus 50. That is okay, because you know that G and minus G gives the same obvious action. Okay. So is there any doubts so far? No? Okay. So this K theta is this thing. Let K tilde is really C, K, C inverse. And this K tilde is of this form, collection of all K theta tilde. So the theta comes to 1. And this is has also a name. And this name is S of U1 plus U2. Okay. So you just take this as a definition. So this K equivalent is really S of Q1 equals to. So now we want to look for the AFP. These are simple exercises. Let's check that. Let 80 tilde, I define something. This is really cos ST, sin ST, sin ST, cos ST. So let's just check that. C 80 CM cos area 80. Where C is that one. Okay, so let 8 implies this is really C 8 CM. And this is the collection of all matrices 8 tilde, which are of this one. Cos ST, sin ST, sin ST, cos ST. So that T belongs to R. And this group I will also name this is the soul not 1, 1. So this is just remember that this is the soul not 1, 1. This is clear. Now the third thing is four. So let NS tilde is the collection of this thing. 1 minus S by 2I. This thing C and S C and S really MS2. So let any tilde is this collection of C and C. So okay. So G tilde is really the straight conjugate of G. So G tilde is homeomorphic to G. Similarly, K tilde is homeomorphic to K, and N tilde is homeomorphic to K. So now using the so-called Iwasawa decomposition of G, which is SL4. So it is clear that you also get an Iwasawa decomposition of G tilde. That is really K tilde, K tilde. So clearly, so using G is equal to Kn, we get that G tilde is equal to K tilde and K tilde G naught. So that is every so you can write that every element G belongs to G tilde can be unique with plus some K1, A1, N1, where K1 belongs to K tilde, A1 belongs to K tilde, and N1 belongs to K tilde, and K1 and A1 and N1 depends continuous terms. That's clear. Now, SO not 1, 1. So do you know the definition of SO 1, 1? SON. Okay, so I will talk about this next. So this has a name and this definition is SO not 1. This is a connected component of SO 1. So, what are these? It will take some time to define this. Okay, anyway. Yeah, SO 1. K action of this K action on the upper axis. So it will be clear from this. Pay some attention here because so we are in situation. So this is step G is equal to SL2. And so G is equal to SU1. SU1 component. Okay. Now if you look at the stabilizer of GI, I belongs to this upper axis. So this SL2 acts on its transitivity. So if you look at stabilizer of GI, you will get this P. Similarly, this SU1, so that will act actually transitively on P because this Kalena is a very conformally code. So this G with G tilde will act on the transitivity. Here. And what will be the stabilizer of so G tilde 0, this is going to be stabilizer of 0 in G tilde. So simply this will be K tilde. You know that what is K tilde. Okay, so if since SL2 acts on is transitively and stabilizer of I is K, and this action is also continuous. Okay, what does it mean? If you look at this thing map, so this action is continuous. If you look at this map, G or Z going to this G dot Z. So this is map from G cross H to H is continuous. So this action is continuous. So that means this thing. So that means this that will give you that G mod K is really homeomorphic to H. You have studied, I think you have studied. So this is a homeomorphic. In fact, it is more, much more than homeomorphic. But if you are not, if you know this differential geometry, then this is actually different. So similarly here, actually you will get G tilde, K tilde is homeomorphic to B. Now, so we have actually started what is the A action. So this is the picture in this SL context. This is the picture in say SU11 and B case. This is upper axis. So this is my upper axis. So this is my IC. And that maps to the unit this is calendar, and this is really C of I. Okay, this is really C of 0 and 0, C of infinity. Now, what is the n orbit here? N orbit here actually is a very just parallel. These are really horizontal lines which are really parallel to the real axis. Okay. And we want to really find what is the n tilde orbit here. So this is an n orbit and this is an orbit. So because n tilde is really a conjugate of n by this so-called by C, by the this element C. So n tilde orbit will be exactly those which are the image of these lines under calendar. So what I am saying that we know these n orbits are really horizontal lines. These are really parallel to the real axis. So n tilde orbit in this picture, okay. So that will be really the image of these lines under this calendar. And calendar is a Mobius graph. So that takes circle to circle. And this line actually is a line, or you can take a circle that passes to infinity, right? So in that picture, that will be a circle that will passes to this C infinity. Okay? And that will be inside the unit list P. So that means that will be something, this will be some circle inside the unit list, and that will touch the point C. That is clear. So now what is the so what will be image of this line under this column? That will be also a circle which will pass the same way. But since these lines are parallel, that will be also a parallel circle. This is it. So what I am saying that n orbits and n tilde orbits in this picture will be something from parallel circle. So this type of circle. So I hope this is clear. So these are really in so this is n orbit and this is really n tilde. So now I want to draw, or I want to say what is A orbit. So A orbit, where what? This is a thing. And suppose this is an A orbit which passes through I, and this is an also A orbit, and this is also. Now, yep. This is my so this is my picture. This is my C of minus what? This is my C of 0. Yeah, C of 0. This is C of 1. And this is C of 2. So let's listen to this very carefully. So and this is really, these are my A orbits. A orbits are really rays which starts from the origin 0. Okay, so image of these rays will be my A tilde orbit. Okay, so look at this line. This is a really a circle that really passes through 0, I, and infinity. So the image of that will be a circle that will pass through C0, Ci, and C infinity. So that means this line will go to this. Is clear? So this will be a tilde. So this will be a. This is an tilde. Now, similarly, this line actually passes through this 0 and infinity. So that will be a circle passing through C0 and C infinity. So that will be and there is K tilde. So I will take 5 minutes. So for this thing is equal to, remember I told you that in this SL2R case thing, K epsilon H is not very nice. But N and A epsilon are nice. So now if you look at this thing K theta is equal to what e to the power minus K theta tilde in this picture, 0, 0, 0, and that will upturn Z clearly e to the power minus 2. And so this is my next picture. So if you take this something like Z, so what will be the K tilde orbit? That will be really circle, right? There is circle will be passing through this thing. Of radius more, something like this. Okay, this is the K, and these are really K tilde. This is the K tilde. Okay, so now this on this L2R models. So this is my thing. This is my picture. So what will be K tilde orbit there? That will be basically image of this circle under this maps. C inverse is the map from this to this. And since this map actually takes circles to circles, so K orbit will be really circle. But K orbit will be circle. So these are really K orbit. These are really K orbit. And since 0 lies inside this, 0 lies inside the circle, therefore this I point I will lie inside the circle, but I may not be center of the circle. So K orbit images are in circle with I imaginary. I may not be the center of it because no base now doesn't really preserve the center. The center of it. So this is one thing. I just want to finish this so-called K decomposition. So now, observation. So, from this picture, actually, first observation. Now, we have got this thing. You also have a decomposition for this thing. G is equal to SL2R and G is equal to SU1, and we have proved that G is equal to K and G tilde is equal to K tilde, A tilde. This is not really specific to so-called SL2R or SU1. So this is also true for any connected semi-simple linear or non-compact semi-simple linear. And I think now onwards I will not use this symbol G tilde for this SU1. So if I am saying that G is equal to S21, 1, then you also understand that this K is in this picture is really S of U1, 1. So I will not use this G tilde, K tilde. So I will fix a group like SU1, 1 or SU1. And in that picture I will talk about K and A and Q. And it will clear from the concept which group I am taking. So G is equal to I am taking SU, 1. So first thing, first observation. So G is equal to SU1 and D is the thing. Observation. If this thing happens, Z1 and Z2, if mod Z1 is equal to mod Z2, then they will lie in the same orbit, and then there exists some K belongs to K, and K is here S of U1 because there exists K belongs to K, so that this K Z1 is equal to Z1. This is clear. Now suppose so second thing, let Z1 and Z2 belong to D. Okay, so suppose mod of Z1 is equal to mod of Z2. So that means if Z1 and Z2 mod of Z1 and Z2 same, they will actually lie in the same K. So this is my Z1 set, this is my Z2. So that means there exists some K which will take Z1 and Z2. Assume that 0 is not equal to Z1, not equal to Z2. So how many K's? So there exists. So there exists some K belongs to K. K theta belongs to K. So that K theta Z1 is equal to Z2. The question is whether this K theta is unique. And that is not unique, right? Minus K theta is also. But my claim is there only exist exactly 2 Ks. Okay? So that this K theta Z1 is equal to Z2. So observe that there exist exactly 2 Ks so that there exists exactly 2 elements K1 and K2 belong to K with K1 is equal to L minus K2 so that this K1 or Z is equal to Z1 is equal to Z2 is equal to minus of K2 Z2. There will be one rotation and other rotation is theta plus phi. That will correspond to that. Now, that is I will just finish this K decomposition. Otherwise, there was very okay, so this is the thing 0 and this is very minus 1 to 1 and this is an AR. This is an AR. We have discussed it. So if you look at this thing, So what is 80.0? 80.0 is using this minus cos st, sin st, cos st dot 0, and this is really tan st. Now this t going to 80 tan st, and that is really 80.0 is a homeomorphism from R to minus 1, right? So that means if u 0 minus 1 less than 2 less than 1, so that is the R. There exists a unique t belongs to R, so that this thing u is equal to very 80. So second thing, observe that u is greater than or equal to 0 if and only this t is greater than 0. And this is important. This is a unique t belongs to R. And this is this. Now we want to prove something called we want to prove something called k a plus k a. Okay, so let A plus is the closure with the collection of all T, so that T is the connection. Okay, so now this is the thing. First fix. Okay, so G belongs to G. So that means let J is equal to N G dot G. So by this thing, by this observation, there exists a yeah. Okay, so I am writing. I am writing this thing, sorry, because you get there exists a unique t greater than or equal to 0. So that u is, so by this this is called this star. This by star there exists a unique t greater than or equal to 0, so that this mod z is equal to really a t dot z. This t is really. Okay. Now that means since mod z and z has the same value, okay, so this mod z and since mod z and z belong to the same k orbit, by this by this double step, so by this double step, there exists a k belongs to k, so that k dot mod z 80 dot g. So this k may not be unique, but we will discuss when that will be unique. So mod of k of dot mod z is equal to 80 dot 0. Oh, k dot, sorry. Oh, by double step there is a k belongs to k, so that k dot mod z is equal to 0. So k dot mod z is equal to, and k mod z is what? 80 dot 0, right? and J is equal to 0, 0. So what I am getting here? So by that thing, I am getting k dot t dot 0 is equal to 0. Okay. 0 is equal to 0, 0. And this t is unity. So if you take this, so k t inverse g dot 0 is equal to 0. And this, since this stabilizes 0, so stabilizer of 0 is k. So this implies k t inverse g is equal to k1 or some k1. So g is equal to k k k, and this t is really determined equal to 0, and this t is unique. So what I am getting is thus I am getting g is equal to k across all of t. So this is it. Now remark about the uniqueness of this decomposition. So we are getting this t is unique from here, but we will get only unique decomposition if this k is unique. Yeah. So just but here you see that if z is not equal to 0, but if just one so if z is not equal to 0, that means this is equivalent to this fact that g is not belonging to k, because g dot 0 is not equal to 0. That means g is not equal to k, then there will exist two different k's, and therefore so okay, so you can okay, so I am writing the statement. Okay, so you can check this. So if g is equal to 0, so g is equal to the conclusion. I am writing the conclusion. Now if g doesn't belong to 0, then g has exactly two equations. That is g is equal to k1 k2 or s minus k1 and t greater than equal to 0 and t is 0. Tomorrow and we will see the geometry of hyperbolic space, and day after tomorrow we will